Welcome back everyone. In this section we will learn about alkenes and alkynes. Alkenes are those hydrocarbons which contain one or more carbon-carbon double bonds. On the other hand, alkynes are those hydrocarbons which contain one or more carbon-carbon triple bond. For example, this is an example of an alkene. Let me write it in expanded form. On the other hand, this molecular formula represents an alkyne. Both alkenes and alkynes are classified as unsaturated hydrocarbons because they have fewer than 2n+2 hydrogen atoms. In this formula, n represents the number of carbon atoms. For every one double bond, the alkenes will have two less hydrogens, and for every one double bond, alkynes will have four less hydrogen atoms. As learned in previous slide, alkenes are those hydrocarbons which contain at least one carbon-carbon double bond. An example of a simplest alkene is shown here. This alkene contains two carbon atoms, and as we can see that it does contain a double bond, and hence it is classified as an alkene. In chapter number 4, we learned that if an atom has three bonding sites, as in the case of alkenes, as you can see that each carbon atom has three bonding sites, and in chapter number 4 we learn about the geometry around the atom which contains three bonding sites, and we learned that in this case the geometry will be trigonal planar. So therefore carbon atoms in alkenes which contain a double bond are trigonal planars, and we also learned that the bond angles in trigonal planar geometry is 120 degrees. So therefore alkenes where the double bond is present, the bond angle will be 120 degrees. The ball and stick model of our simplest alkene which contains two carbon atoms is shown here. The name of this alkene is ethene. It is also known by its common name as ethylene. So ethylene is its common name, whereas the standard name is ethene. Let's learn how to draw the structure of alkenes. As usual, we can use Lewis structures to show the structure of an alkene, but however, we learned that the drawing Lewis structures, especially in case of longer carbon-carbon chain molecules, can be quite complex. So therefore, we use condensed structures. So in case of alkenes, again, we can use a skeletal line structures as well as condensed structure. In skeletal line structure, as we learned that we do not show carbon and hydrogen atoms, we only show the bonds. In a skeletal line structure, a double bond is drawn as two parallel lines as shown in this case of 1-butene. In case of 1-butene, we have four carbon atoms. So that's 1, 2, 3, and 4, and we have a carbon-carbon double bond between carbon number 1 and carbon number 2. So in skeletal line structure, we simply show the double bond as two parallel lines, and the rest of the skeletal line structure is shown as usual with a zigzag pattern of lines. Remember, each connection point within the zigzag line shows a carbon atom, and the end and the beginning also shows a carbon atom. And number of hydrogen atoms can be calculated based on how many bonds are already connected to the carbon atom. In case of condensed structures, the double bond of an alkene is inferred from the number of hydrogen atoms on the carbon group. For example, a Lewis structure of 1-butene is shown here, and as you can see that at carbon number 1 and carbon number 2 we have a double bond. So when we write the condensed structure, we do not show the double bond or even single bonds, we only show the carbon atoms and hydrogen atom. But we can see that carbon number 2 contains only one hydrogen atom. So from that we can figure out that there is a double bond between the carbon 1 and carbon 2. So this is the condensed structure of an alkene. The other method is that we do show the position of the carbon-carbon double bond. However, other single bonds are not shown. I prefer to use this notation because in this case it is easier to see where the double bond is, but in many books and many other places you may encounter the condensed structure of alkenes where the double bond is not shown. So in that case you have to be very careful to figure out whether there is a double bond present or not. The IUPAC rules for naming straight chain alkenes and unbranched cycloalkenes are similar to the rules for naming straight chain alkanes and cycloalkanes with some slight modifications. Let's learn about those modifications. In case of straight chain alkenes, we count the number of carbon atoms in the chain as we did in case of alkenes, and then we assign the name based on the number of carbon atoms, and the name ends with ene, E-N-E, because ene comes from alkene. For example, if we have alkene with the 3 carbon chain as shown here, we know the name for 3 carbon is prop, and then it will end with ene, so it would be propene. However, propene is not the final name. There is one modification to the name which I'm going to explain right now. So once we figure out the number of carbon atom, and based on the number of carbon atoms we know the name of alkene, the next thing we need to do is we need to number the chain from the end which is closer to the double bond. So in case of alkene we will number it from left hand side because that's where the double bond is closer. So that would be 1, 2 and 3. From the number we add the locator number to the beginning of the name corresponding to the number of first carbon of the double bond. So what do we mean with that? So what it's saying is that whichever carbon atom begins with the double bond, that's the locator number of the double bond. So in case of propene, the double bond starts at carbon number 1. So the locator number for double bond in case of this propene is 1. So hence the proper name would be 1 and then hyphen propene. So this is the correct name for 1-propene. So let's look at this example. So in this case we have 8 carbon long alkene. So from 8 we get the name oct, and because there is a double bond, so therefore it's ene, so it's octene. So now the locator number comes from the numbering of carbon atom, and remember we number from the side where the double bond is closer. So in this case the left hand side has the double bond, so therefore the number locator number for double bond will be 1. So hence this alkene is 1-octene. I would like to clarify here that the double bond can also be present in the middle of the molecule. It doesn't need to be on the end. For example, let me erase. For example, we may have a alkene where the double bond is somewhere in the middle. So now in this case also, let's count the number of carbon atom, and while we are counting it, let's give the numbers also. So as you can see that if I count from left hand side, so I get 1, 2, 3, 4 and 5. So that would be my numbering. But if I count from the right hand side, it would be number 1 here, number 2 here, number 3, number 4 and number 5. So as you can see from left hand side, the locator number for double bond is coming out to be 2, but from right hand side the locator number is coming out to be 3, and we want to give the smallest locator number possible. So therefore counting from the left hand side is the correct order and counting from the right hand side is incorrect. So let me erase the incorrect order. So now we know the number. So we have 5 carbon atoms in the chain. So name for 5 is pent. Because there is a double bond, so it's an alkene, so it would be pentene. And the double bond locator number is 2, so therefore it is 2-pentene. In case of cycloalkenes, we count the number of carbon atoms within the ring and assign the name with the cyclo prefix and "ene" at the end. For example, in this case, if we count the number of carbon atoms, it will be 1, 2, 3, 4, 5, 6, 7 and 8. So therefore the name comes from 8. 8 is oct, and because it's a cyclo alkene, so it will be cyclo, oct and ene. Ene specifies that there is a double bond. Although we used a locator number for straight chain alkenes, however in cycloalkenes number 1 always is given to the carbon where the double bond starts. So it is understood that the double bond is at number 1 locator, so therefore no locator number is used. So this is extremely important because it is understood that locator number for cycloalkenes is 1. We always count from the double bond. So therefore it is understood. So therefore no locator number is needed in case of cycloalkenes. Let's name these alkenes. So in first case, uh, we need to count it. It's a straight chain alkene, and we can see that the double bond is on the left hand side, so therefore we will count from the left hand side. So that'll be 1, 2, 3, 4 and 5. So 5 means the name is pent, and because it's an alkene, so therefore it will end with "ene." Locator number is 1, so it is 1-pentene. In example B, we have a cycloalkene. Remember, we count from the double bond, so it would be number 1, number 2, number 3, number 4 and number 5. Again, it's a pentene, but it's a cyclopentene because it's a cyclic alkene. So cyclopentene, and no locator number is needed here because it is understood that carbon-carbon double bond begins at number 1. As we learned that alkenes are those hydrocarbons which contain a double bond. In some cases, we may encounter an alkene which may have more than one double bond as shown here. So in this example, we have 3 double bonds present within the hydrocarbon. So an alkene which contains at least 2 carbon-carbon double bonds is known as a diene, and if an alkene contains several carbon-carbon double bonds, it is called polyene. So the example here, which I have shown here, it contains 3 double bonds. So this kind of alkene is known as triene. Tri means 3 and ene means it's an alkene. So it's a triene. But if it contains more than 3 or several carbon-carbon double bond, then we simply call it polyene. Poly means many and ene means alkene. Fruits, vegetables, spices, and many other natural products contains polyenes. For example, a polyene such as beta carotene is common in carrots. In fact, that's why the name of this polyene was given to be carotene, because it's found in carrots. Uh, let's identify if the alkenes shown here are simple alkenes, dienes, or polyenes. In example A, we can see that this alkene contains two carbon-carbon double bonds. And if an alkene contains two double bonds, then it is known as diene. Di means two and ene means alkene. So it's a diene. In case of example B, it's a cycloalkene, but because it contains only one carbon-carbon double bond, therefore it is a simple alkene. In example C, it has a three carbon-carbon double bonds. You can call it a triene, or it can also be classified as polyene. Although carbon-carbon single bonds are able to freely rotate around itself, and that's why alkanes form multiple conformations. However, rotation around the carbon-carbon double bond is not possible. Consequently, two alkenes with same chemical formula and same connectivity of atoms, but a different three-dimensional orientation above the double bond, are different compounds, and these compounds are known as geometric isomers. So as shown in this picture, because going from left hand side to right hand side is not possible, so therefore the compound shown on the left hand side and compound shown on the right hand side, these two compounds are different molecules. Why they are different molecules? Because their interconversion is not possible, because rotation around the carbon-carbon double bond is not possible, so therefore they cannot be interconverted into each other, hence they are different molecules. So these kind of compounds where molecular formula is same and connectivity is also same, however they are still different molecules, so these molecules are known as geometric isomers. Why they are called geometric isomer? Because their three-dimensional orientation or geometry is different. That's why they are known as geometric isomers. So alkanes do not show geometric isomers because rotation around the double bond, rotation around the single bond is possible, so they interconvert into each other. However, only alkenes and alkynes can show geometric isomers. An example of pair of geometric molecules is shown in this picture. Both the molecules shown in this picture represent 2-butene. As we can count, in both cases we have a 4-carbon chain and the carbon-carbon double bond is at number 2, so therefore in both cases it is 2-butene. However, you can notice that in the example shown on the left hand side, both hydrogen atoms are present on the same side of the double bond, which is below the double bond, and the methyl groups are present on the other side. So if similar groups are present on the same side, then that geometric isomer is known as cis isomer. So therefore, geometric isomer shown on the left hand side is a cis isomer. On the other hand, the isomer of 2-butene shown on the right hand side has the similar groups across the double bond or on the opposite side. As you can see, even the hydrogens are present on the opposite side of the carbon-carbon double bond. So those geometric isomers in which the similar groups are present on the opposite side of the double bond are known as trans isomers. If you read any food nutritional label, you will find that our food contains two kinds of fats. It can be either a saturated fat or it can be an unsaturated fat. Saturated fats are those fats in which we only have carbon-carbon single bonds. A molecular formula or a structure of saturated fat is shown on the left hand side, and you can see that if this molecule uh, contains a structure in which we have three long carbon-carbon chains, and in all of these three chains there is no double or triple bond present. So this kind of a fat molecule is known as a saturated fat molecules because all the carbon-carbon chains are alkane chains. On the other hand, in case of unsaturated fat, at least one of the chain, maybe more, will contain a double bond somewhere. It may contain multiple double bonds, but at least one double bond will be present. If in a fat molecule uh, or a double bond, at least one or more double bonds are present, then that fat is known as unsaturated fat molecule. All the unsaturated fat produced by uh, natural organisms, either plants or animals, will mainly contain cis double bonds. So as you can see, all these arrangements are cis arrangements. Trans unsaturated fats are not generally produced by natural sources. The overall shape of cis uh, isomers present in the unsaturated fats will cause the packing of these molecules to be loose, which results in lesser intermolecular interactions, and hence unsaturated fats are normally oils. They will have low melting and boiling point, so therefore they will be present in liquid state, so hence they are oils. No such bend is present in the saturated fat, so all the chains are kind of linear to each other, so they can be packed really closely. Hence saturated fats have strong intermolecular forces, so hence saturated fats will be solid at room temperature. Example of a saturated fat is butter or lard, and as we know that both butter and lard are solid at room temperature. Example of unsaturated fat is olive oil or canola oil, and most of the oils are examples of unsaturated fats, and we can see that they are liquid at room temperature. Let's identify cis and trans isomers shown in these structures. In example A, the isomer shown on the left hand side has a similar groups on the bottom. Uh, Although it's not shown, but we understand that there is hydrogen atom here and there is hydrogen atom here because there are three bonds already present on these carbon, and you can see that hydrogen atoms are also present on the same side. So hence this isomer is an example of a cis isomer. And the example shown on the right hand side, as you can see that the carbon here and here, they are opposite side, and there are hydrogen atoms not shown here because it's a skeletal line structure, but it is understood that there are hydrogen atoms, so they are also present across. So therefore this is an example of trans isomer. Now in B, although you may tend to think that, oh, in this case also they are on the same side and it's opposite side, however there is no double bond present, and we know a single bond can freely rotate, and when they rotate they can interconvert into each other, so hence these two are same molecules. They are alkanes, so they are same molecules.